confident. What does that really mean? So, if you had to put it in words right now, how would you say it? Yeah, exactly. I would chuckle and reach for a glass of wine. Let's save this, shut her down. If you had to tell me right now what you thought a set of 99% confidence was, what do you think? How would you describe it to your neighbor? I always like to think of this as, you're out, beautiful weather, right? You're out doing yard work in your yard. Your neighbor comes out, you both cut the grass, you do little real mowers, chit-chatting. How's work? Well, work's great. School's good. What about confidence yesterday? Confidence? What's that? How would you explain it to your neighbor? If you had to explain confidence to your neighbor right now.
On average, 99% of the time, I will hit between these two numbers.
You're this close. That's what Steph said earlier. You guys are this close. Here's the deal. You have to remove those two numbers from your description because those two numbers only talk about your sample you just did. So you guys are so damn close to what the correct... Watch this. Okay, here's a little Excel. Let's hope this works. I just made this up. I hope this works for you guys. I've got a population. I tried to make it kind of skewed because what the hell? We can never know about populations. We have no idea what they usually look like, right? They're usually pretty skewed, or at least skewed a little bit from bell-curved. Different. The sampling distribution, of course, is always perfectly bell-shaped by the central limit theorem. We know that for a fact. And that thing has an average. Now the idea is, when you make a confidence interval, which I've indicated here in green, you are trying to capture the average of that population with the interval. So you're hoping that this interval does what? Contains what?
The average.
Good. Hoping it contains that purple line. It looks like this one missed it. So if I press F9, I will draw a new random sample. And you see what it's doing is it's keeping track of, did I catch it or did I not? Did I catch it or did I not catch it? Okay, sometimes it does. It just did right there. Now you gotta remember something, friends. You gotta remember something. Most of this picture you'll never see in your statistical life. You will see this green line much the same way we just saw it over here. We caught it, right? We caught this and this. That's our confidence interval. Are you gonna see this big gray curve up here? No, that's the population curve. It's a deck of cards. You can't see it. It's out there. Are you gonna see this bell curve? No, because that's a function of that gray distribution. Are you going to see this purple thing? You don't know that either, do you? Crap, we suck. No, we don't. No, we don't. Because we know this. Now, what I want you to do is I want you to look at that percentage that's right there in the middle. Cumulative probability. How often does it look like that interval is catching the average? I got over 32%, yes, and if I hold down F9 and let it sit there for a while, we'll get a more refined estimate. So it catches it about 33% of the time. What would we say about the confidence level of that interval? What confidence are we operating at? Approximately 33%. Do you see what confidence means? It tells you on average how often you catch what you're trying to catch. You don't have to mention the interval you just calculated. As a matter of fact, you shouldn't. You're going to talk about confidence without ever using data. 99% confidence means 99% of the time when you create one of those, you're going to catch the parameter you're looking for somewhere in the interval. One out of 100 you're going to miss. That'll be an outlier sample. 95% confidence means that 95 times out of 100 you're going to catch what you're looking for. 33% confidence means roughly you missed 2 out of 3 times. Is that pretty inexcusable? Yes! Let's increase our confidence-o-meter. Let's increase the confidence-o-meter. What happens to the confidence interval as I increase the confidence-o-meter? Did you notice what was happening to it as I increased the confidence? What happened to the interval? I call this the Carly clause. What happened to it? McKinnon, go! It got wider! Because when I increase the confidence-o-meter, what I'm essentially doing is I'm making this number bigger. which stretches the interval out. Watch what happens to, oops, sorry, I click out here. Watch what happens to my percentage of confidence after I've done this. What's happening to it, friends? It's getting larger. Why is it getting larger? Because I'm catching what I want to catch more often. Now you got to remember, this thing has to overcome all those goofy misses before too. I didn't reset it back to 0. So not only is it catching more, it's overcoming all that goofiness. What confidence do we appear to be sitting at about now? We're roughly at 62% now. Is it creeping up any more? 64? It might creep up some more because we have to overcome the original 33. So now we're at 62. What should we do now if we want to be even more confident? Yeah, let's bump that confidence meter up some more. What's happening? As McKenna told me earlier, when we increase confidence, what are we doing to the intervals? You're making them wider. If you make them wider, does it make sense logically why that would capture the average more often? That's, hopefully logically that makes sense. The wider the interval, the more often you're going to be catching the parameter, that you're looking for. The problem is, and here's the problem statistically, you never know where the parameter is. But when you set confidence, you get a very, very powerful tool, don't you? You know that 99% of the time, it's going to be within the interval you've created. You just don't know exactly where. So that's why it's so important to put the plus and the minus on there. Because you know with Carly's 99%, 99% of the time, unless I happen to draw the one goofy outlier case, in the other 99, on average over time, the other 99 out of 100 times, the parameter I'm looking for is in there. I just don't know exactly where. And going back to what Veronica said, remember what Veronica said was so awesome what she said. Since the interval is more on this side of 50% than this side of 50%, can't we say that it's more likely to be there? That was a very specific case in that we were comparing it to 0.5. In general, remember, all you're going to get are these two numbers. So you don't know in general that this purple line is on this side of your p hat. It might be on this side of your p hat. It might be way over here. It might be right at p hat. Who knows? All you know is 99% of the time, it's between those two values. Let's see how our confidence did. Let's see how our confidence did. Okay. How we doing now? Oh, did I ever increase it?
Yeah.
I did. I'm gonna pop it up some more. I'm gonna max it out. There we go. There we go. How we doing now? Why is it not updating? Oh, there it goes. Oh, it's got to make up. Well, you can see how it's updating right now. The numbers have to catch up. See how only the yeses are increasing right now? Every single one is catching it. Go ahead, please, Cassidy.
So then, why would you ever do lower than 99?
This was the question I was hoping would come up today. Why in God's name would you ever do any? Why wouldn't you go to 99.99999999999?
Because if you're wrong, you need something to back that.
Well, okay, I wasn't thinking that, Austin. Austin's got a good point. If you're wrong, then you're really screwed, because then you've got an egregious case. If you get too wide, if your interval gets too wide, it becomes practically useless. And here's what I'm talking about. Suppose you go out to 99.9 repeating confidence. Eventually you're going to get to a point, there's a point of diminishing returns where you go, okay, I am 99.9 repeating confident that the percentage of decrease of pain using my medicine is between 0 and 100%. Because that's what's going to happen eventually, right? Think about it. If you bump that interval out wide enough, eventually it's going to bottom out at 0 and top out at 100%. And it becomes practically useless because you lose all precision. You got perfect accuracy. Essentially, you're at 100% confidence then, essentially, because you've covered the entire number line. But the researcher then goes, but I don't get it. Like, that doesn't tell me anything. Does that make sense? So then there becomes this fine line of, okay, so I want to be more confident than less, but how much is enough? There's something that makes it difficult. And I'm going to plant this seed in your mind now, and we're going to come back to it later on in the course. There are two ways to be wrong, and you've already looked at both of them. On the first day of class, when you pulled the cards out of the deck, and you guys made a claim about my deck, you said it was fake. And you could have been wrong, yes? And that would have been a false positive. Saying it's wrong when in fact it's not. What's the other way to be wrong? A false negative. Mathematically, this is one of the most interesting results, I think, in Math 244. Mathematically, as the chance of a false positive goes down, which would be increasing confidence. If you increase confidence, your chance of a false positive should go down. This goes back to what Austin was saying, but you gotta explain yourself then when you do get a false positive. So if you're at 99% confidence, that means you're wrong 1% of the time. If you're at 99.9%, that means you're wrong 0.1%, and so forth. The chance of missing or a false positive goes down. The chance of a false negative actually goes up. What? How can that be? You're going to see mathematically in this class why that is. So you want to balance those things. I often ask it like this. How many of you guys have been to Yellowstone National Park? Yellowstone National Park? A few of you? When you were there, did you go to Old Faithful? Why'd you go to Old Faithful? Because there's a parking lot right next to it. Why'd you go to Old Faithful?
To watch it.
Why'd you go to watch Old Faithful?
Because we knew eventually it was gonna.
Good! It's called Old Faithful for a reason. Because it faithfully erupts. I think it's everywhere. You guys studied it. I gave you a quiz last term, didn't I? On Old Faithful eruptions? I circulate that one through every couple terms, right? Good. Every like 65 to 90 minutes or something like that. I think I talked about this before. There's a geyser in Yellowstone called the Minute Geyser. I told you about this, right? The Minute Geyser, right? It goes off every minute. So why not just go to see that one? It goes off every minute.
It's tiny.
Because it's tiny. So Old Faithful is also large, but there's a larger geyser called the Texas Geyser, right?
But it's not consistent.
But it's not consistent. Old Faithful is the perfect blend of consistency and size. Just like 95% seems to be the perfect blend between minimizing both kinds of errors. So, Cassidy, your question is awesome. It's not answered easily quickly. But to plant that seed in your head, there is another kind of wrong that you want to avoid. It's called a false negative, which these guys don't approach yet. Hypothesis testing definitely gets into them. Fair? Good, 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 good. Other questions? That was a fantastic one. Alan, go.
This only works for binomial distributions, though, right?
For percentage data, yes. Alan asked the question. This only works for the binomial distribution, yes. And the answer to that is yes, indeed. It only works for binomial distributions when you're talking about discrete data like this. Once we put continuous data in, it won't work for those guys at all. We'll deal with those together on Thursday. Other questions? These are great. Now, we're almost out of time. I'm going to send you guys home with this. This is an in-class quiz. But what we'll do is, we'll just send you home with it to practice it. We won't have time to get through the entire thing. We can start it today. We can start the first one if you want, just to kind of get a feel for it, and then send you home with the rest of it and bring it back and discuss it first thing on, here, grab one of these and send them back. Here you go, here you go. Let me take one copy so I can read off of something. It's essentially just, it's some more data I pulled. I feel that you're getting tired of the penny spins. Oh, speaking of the penny spins, it appears, based on my historical data, that the percentage of heads is actually much less than the percentage of tails. I say much, at least 6% less, yeah? Something like that, 44%, about 6% difference, ignoring the margin of error momentarily. Why would that be? Why would it be that we get fewer heads on a coin spin than we get on a coin flip? Any ideas? There's more. This is my vote. The heads side is heavier. This is my vote. That the heads side is heavier. The head side is heavier. Now, how would that result in fewer heads if the head side is heavier?
Go down.
It keeps spinning. You ever heard of something called inertia? Physics, inertia? What is inertia in conversation? Object in motion tends to stay in motion. Thank you, Jolene. Good, and that's the whole point of the, thank you. That's why a coin flip is different, yes? Coin flip, oh grab, oh slap. Upon two forces. A coin spin, no action. That's why I was so careful about where you were spinning. Make sure there are no external forces. That's why I was kind of nervous with these tilted desks. I was nervous about that. And as I'm doing this, there are little eraser things on here that maybe butterfly effect that could affect the results too. So the idea is a coin spin is pure physics being applied to that penny. Which means the heads and the tail side are both spinning. But the head side has more mass, therefore it has more inertia. My vote, therefore, is it wants to keep spinning longer. And the tail side gives up first, and eventually the head side spins itself down, which means the tail side is sitting up. Physically, that makes sense to me. Carly, go ahead.
I just have a quick question.
Yes!
Oh, it's just a question of where the 2.575, like the 99%, and like, is that online?
You don't need to do it. That's the whole part of putting that oh, well, it's in the spreadsheet.
Yeah.
Or the PowerPoint.
Okay, yeah.
And you'll have that. It is, oh, sister, it is totally it's everywhere online.
Right.
It's also in your Stenormal program.
Okay.
It's there. I mean, basically, all it is, all it is it's a result of the Stenormal calculation. Yep. It's extraordinarily prevalent online.
Okay.
But you'll also have that little cheat sheet table in this PowerPoint that'll be posted. I think I posted it last time for you guys. It's sitting in there waiting for you.
Okay.
Yeah, by all means, yeah. But the thing is you don't need to memorize them because technology takes care of them for you. In the coding for the confidence intervals, it automatically feeds in those correct values. But if you ever need them, they're there waiting for you in that PowerPoint and online and everywhere else.
All right.
Cool? Great question. Okay, now what I want you to do is, I want you to look, let me stop this again.